The cosmic microwave background radiation and other large-scale structural studies have shown that this mystery energy is truly real, but new findings made by the James Webb Space Telescope have made people question the idea of dark energy. The JWST can look at the early universe with more accuracy than was possible before. The standard model of cosmology says that structures and objects should be younger and less developed than they were when the first detailed observations were made. It's possible that these findings show that the universe may have started earlier or expanded even faster than was thought before. All of these findings show that we still don't fully understand some important cosmic elements and forces, such as dark matter and dark energy. This could mean that the normal model of the universe needs to be completely rethought. That's not ready for us yet, though. We can't come up with new theories because we don't know enough about what's new. Will the world of quarks hold the answer? We will have to wait a little longer for the change in the way we see the world. We won't be able to put together a new picture until Webb sends us more pictures and scientists find even more amazing things. It might take a while. For now, researchers all over the world are looking for solutions that are already out there. David Gross is another scientist who is glad about the problem and sees it as a chance. Gross says that the solutions to the universe's big questions are not hidden in the big picture, but in the little picture. A well-known theoretical physicist who knows a lot about string theory and the idea of strong interactions, he is also a Nobel Prize winner. In 2004, he won the prize for finding asymptotic freedom in the theory of strong interactions. The finding was very important for learning about how quarks behave. Quarks are the building blocks of protons and neutrons. The normal model of particle physics is based on these particles, which are the building blocks of everything we can see and measure in space. Because of this, the basic structures and rules of the macrocosm must also exist in the subatomic world. Among other things, Gross helped to come up with ideas about what happened right after the Big Bang. Back then, there were no stars or other things in the world. For hundreds of thousands of years, there was only a very hot primordial soup where particles could move around without sticking together. It's likely that before the Big Bang, there was only a type of quantum fluctuation where all forms canceled each other out to the point where they were physically equal to zero. This quantum fluctuation broke apart with the Big Bang. Particles full of charges and forces shot into a space that wasn't there before. In the end, these bits turned into galaxies, planets, stars, and living things like us. Should we believe Gross when he says that these particles hold all the answers? Most likely, yes. But how can we study how particles behaved 13.8 billion years ago when they were in space? The microwave background energy from space is one thing that researchers use. This is thought to be a pretty good description of what happened right after the Big Bang, and it has probably not changed much since then. Quantum physicists and classical physicists don't quite agree on how to understand this record of the early world. In the world of science right now, quantum and particle physics and standard cosmology can't be put together. Quantum physics doesn't agree with what we know about made matter, or rather, the missing link is quantum physics. David Gross is sure that this bridge can be found in particles and forces that we didn't know about before. He was one of the experts who worked hard to get people from different fields to agree on something before James Webb started the debate. He worked hard to connect quantum physics and general relativity, which he co-authored so that they made sense together. He wanted to bridge the gap between these two scientific fields. Gross's work on asymptotic freedom shows how quarks act when their energies are very high. This is very important for understanding the early world, right after the Big Bang, when energies were very high. His ideas can help us understand parts of the expansion of the world that we don't fully understand yet. That being said, there is some disagreement among scientists because many traditional physicists think that string theory's ideas are too hard to believe. David Gross thinks that the quantum fluctuations in the microwave background hold the answers to all the questions that haven't been solved yet. It's called the Cosmic Microwave Background, CMB, and it can be found everywhere in the world. From 1989 to 1993, the Cosmic Background Explorer satellite was in orbit. It was the first to notice small changes in the radiation's temperature. The Wilkinson Microwave Anisotropy Probe looked into these changes from 2001 to 2010 to see if they showed proof of the Big Bang. The Planck satellite just recently made one of the most thorough maps of the CMB, but researchers are still not sure how to analyze this data. Some scientists say they have found proof of the Big Bang in the CMB, but others think it shows collisions with other universes and the presence of a multiverse. Look at this image. This is a newly discovered early galaxy that existed about 13 billion years ago, but researchers found that this galaxy is far more massive and mature than expected for a galaxy in the infant universe. Well, this is not the first time that Webb has found such galaxies in the early universe. Ever since the Webb telescope began its journey, it has been challenging our standard cosmological theories. Well, the amazing telescope did not stop here. This time, the telescope has revealed a worrying thing about the universe.
Recently, a Nobel Prize-winning scientist revealed that the James Webb telescope has finally confirmed that our understanding of the universe was completely wrong. It is not about big and bright galaxies but more important new observations from the James Webb telescope that have shattered age-old cosmological theories. Let's consider this. One of the pillars of cosmology is that the spatial distribution of matter in the universe is uniformly isotropic. It means that everything looks the same in all directions if you look over large enough distances. This is because the forces are expected to act equally throughout the universe on a large scale and should therefore produce no observable inequalities in the large-scale structuring over the course of evolution of the matter field initially laid down by the Big Bang. Wherever you look, you will find the same density of matter, the same temperature, and the universe expanding equally everywhere. For more than a century, scientists have been developing various cosmological models with the assumption that our universe is uniform in all directions. The Big Bang model, which is the best theory to understand the universe, is also based on this assumption. The cosmic microwave background radiation also shows that the universe is the same everywhere. However, a recent study published on February 6 in the Astrophysical Journal Letters suggests there may be something seriously wrong with this assumption. Recently, astronomers have confirmed that the expansion rate of our universe is not the same everywhere. In this paper, they revealed that depending on where we look, the universe is expanding at different rates. This is a big problem now because if the universe is expanding at different rates in different places, it creates a major problem for astronomers. This new study also suggests that we may be completely wrong about the current estimated age and nature of our universe. David Gross, a Nobel Prize-winning astronomer, said, "We wouldn't call it a tension or problem but rather a crisis." Let's delve deeper into this discovery and learn how the new Webb telescope discovery confirms a crisis in cosmology. In 1929, Edwin Hubble provided the first observational evidence that our universe is expanding everywhere. Using the largest telescope of the time, he discovered that the more distant a galaxy is from us, the faster it appears to be receding into space. This means that the universe is expanding uniformly in all directions. From this discovery, scientists thought that if the universe is expanding, this expansion must have started sometime in the past, which means that the universe must have a finite age. Since the expansion is occurring equally everywhere, by accurately determining the expansion rate, called the Hubble constant, the cosmic clock can be rewound, and the age of the universe calculated. However, before the Hubble telescope was launched, there was significant uncertainty over the expansion rate of the universe or Hubble constant. This value is needed to calculate the age of the universe, estimate its evolution over billions of years, and understand the forces driving it. When the Hubble Space Telescope was launched, it revealed that the universe could be as young as 9.7 billion years or as old as 19.5 billion years. However, this younger value presented a huge problem because it would mean the universe was younger than the oldest known stars. Over the centuries, astronomers have adopted many methods to measure the exact value of the expansion rate, but surprisingly, each method has produced different values. It's as if the universe is expanding differently for different observations. Currently, there are two gold standard methods for figuring out the Hubble constant. The first involves analyzing tiny fluctuations in the cosmic microwave background, an ancient relic of the universe's first light produced just 380,000 years after the Big Bang. Between 2009 and 2013, astronomers mapped out this microwave fuzz using the European Space Agency's Planck satellite to infer a Hubble constant of roughly 67 km per second per megaparsec. The second method uses Cepheid variable stars or supernovae as distant sources. As Cepheids get brighter, they pulsate more slowly, giving astronomers a means to measure their absolute brightness. By comparing this brightness to their observed brightness, we can calculate how fast the universe is expanding. However, this is where the mystery begins. According to Cepheid variable measurements, the universe's expansion rate is around 74 km per second per megaparsec, an impossibly high value compared to Planck's measurements. Initially, some scientists thought the disparity could be due to a measurement error. However, recently Adam Rees, professor of physics and astronomy at Johns Hopkins University, said, "We've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence." Additionally, the new images from the James Webb Telescope confirm that the previous measurements are correct, and the universe is expanding differently in different places. This discrepancy in the value of the expansion rate suggests that perhaps the universe is not the same everywhere. If this is true, then our standard cosmological model would fall apart, as we would be unable to estimate the age and size of the universe with varying expansion rates. The most important question that arises is, what is causing the universe to expand differently in different regions? One intriguing possibility is that dark energy, the mysterious force thought to drive the acceleration of the universe's expansion, is itself not uniform. In other words, dark energy might be stronger in some regions of the universe than others, causing varying expansion rates. Some scientists claim that if the universe is not homogeneous and isotropic, then our understanding of physical laws may be severely limited. Just beyond the cosmological horizon, gravitational forces might act in reverse, light might travel at slower than expected speeds, and unexpected phenomena could even be possible. This new discovery from the Webb telescope has sparked intense debate among astronomers, as the non-uniform expansion challenges one of the foundational principles of cosmology.